We present self-guidance, a method for controllable image generation using only the attention and activations of a pre-trained diffusion model. Without any extra models or training, self-guidance can move or resize objects in generated images, or even replace them with items from real images, without changing the rest of the scene. We can also borrow the appearance of another image, or rearrange scenes into a desired layout. So, how does it work? Let's zoom out and talk about image generation as a whole. In the past few years, the field has seen immense progress by training huge models on huge data sets using huge computers. These models can output very high-quality images that match text prompts. But so much of the complexity of visual data is really hard to describe through text. For example, what if I want to remove this flask, or make this bottle twice as big, or move this orb somewhere else? Clearly, text prompting isn't the right way to do these things. So what is? Let's start by breaking down how text-to-image models learn to convert a prompt like this one to an image like this. Given a prompt and a noisy image as input, these models learn to predict the noise that was added to the image. Their architecture combines image processing operations like convolutions with text-image correspondence using attention. Recent work has found that the attention operation, a key building block of modern generative models, learns to map from parts of the text prompt to parts of the image canvas. It also turns out that the features of the trained model capture rich information about visual appearance. Our key insight is that by manipulating these model internals in the generation process, we obtain a new type of control over the images our model outputs. As we sample a new image from our trained diffusion model, we can incorporate additional information, sometimes using other supervised models, into each sampling step. This is called guidance, here denoted G, and it's how techniques like classifier or classifier-free guidance work. Self-guidance also uses guidance, but instead of using an external classifier or text prompt, it guides the attention and features of the diffusion model itself to satisfy certain properties. For example, we can guide the center of the attention region corresponding to the word burger to the left, resulting in an edited image like the one shown here. We can also stretch the burger attention region to be twice as tall, or guide the features of the ice cream region to match those of a second image, here turning the ice cream cone yellow. We find that guiding 4 simple properties of the model internals, attention centroid, size, and shape, as well as feature appearance, gives us lots of control over image generation. We can compose these 4 properties to express many different kinds of image edits. For example, starting from generated images, we can move objects around or resize them simply by guiding the position and size of the relevant text attention map as desired. By guiding the shape of all objects to stay the same, but letting appearance features vary, we can sample new looks for scenes with the same layout. We show results from prompt-to-prompt and depth condition control net for comparison. We can also combine the layout of one image with the appearance of objects in another, or only constrain appearance to stay the same, leading to new arrangements of the same objects. Further, by extracting model internals from real images, self-guidance can even copy the appearance of real-life objects into new contexts. Here we use self-guidance to generate a dog and a teapot in different settings, and compare it to Dream Booth, which, unlike self-guidance, requires both fine-tuning and multiple images of the subject. Self-guidance isn't limited to editing generated images and can be applied to real images as well. Please see the paper for more details. Finally, we show that we can also guide verbs and adjectives to make fine-grained changes to generated scenes. We can even use self-guidance to fix attribute binding errors in images generated by our model. For more results, as well as a demo with code, please check out our project webpage. Thanks.